Morning, everyone. So we continue today with our lectures on fundamentals of machine learning with the application using the tools of artificial neural network. And we will talk especially about elementary connectionist models, such as the McCulloh Pitt model, such as the Perceptron, before we go and tackle multi-layer perceptron, more complex structure of neural network. Let me link here to one particular slide we discussed before when we discussed the area of machine learning systems. And I would like you to remember when we spoke about supervised learning, two major tasks we thought needs to be developed. The first one is classification between two type of classes or between multi-classes. So here it's to visualize things. We are utilizing two type of classes, class red and class blue. So that's basically one aspect of supervised learning. The second one is to develop a regression model that is able to interpolate between various points, which we have extracted from sensory systems or from other type of data, and we would like to create mapping that is able to predict all the features of the what links between what links these particular type of points, similar to the red line in this particular example. So that's what we discussed last time. And then we went further and we discussed about the various type of algorithms that people have utilized in the supervised learning. So we spoke about decision trees, we spoke about naive Bayes classification, we spoke about support vector machines, and also we spoke about artificial neural network. And I mentioned to you last time that we are going to focus especially on artificial neural network. And then I will talk also about support vector machine, given their importance and their ease of use, because there are a lot of tools out there that could be utilized for support vector machine. So we are going to continue today on the fundamentals or artificial neural network. And we are mostly tackling the aspect of a neural network where the data is being provided to an architecture, to an engine, which is going to provide us with a decision-making process in the form of either a boundary that is distinguishing between the category outputs, or it provides us with two-dimensional or multi-dimensional type of mapping that is able to reproduce the connection between various points that we have selected or we have obtained through data gathering process a priori. So we are going to talk about artificial neural network. Why is that? As I mentioned to you in the past few lectures, because of major growth of one particular content of artificial neural network, which are deep learning. So we are going to go from the simplest case of artificial neural network to the more complex case, such as the multi-layer perceptron, to go to later on to deep neural network systems. And I will provide you with various aspects of these type of connectionist modeling. So let me go back now to the lecture that we started last time, and here, so let me check this file here. Okay. So this is what we discussed last time in the form of features or of artificial neural network. So we said that a particular structure, similar to the one in this picture here, has several types of components, and the neural network in general is characterized by the flow of information from the input to the output, whether there is feedback or not, by the topology, which we call topology or architecture or the structure of the neural network. We also discussed the elements that are composing this neural network, namely the activation function. And we are talking today about the learning algorithm. So I will go to that component that we discussed last time. So all these are the three major components that characterize a connectionist modeling. So every connectionist model system is characterized by an architecture, by an activation function, and by a learning paradigm. So in the learning paradigm here, we did not mention the deep learning structure because it is part of supervised and unsupervised, as we are going to talk about it later. And deep learning is not part of the major features of artificial neural network. So this is the topology. So we spoke about topology, and then I spoke about activation function, whether they are binary, whether they are differentiable type of activation function. And then we spoke about the learning paradigms, and learning paradigms could be supervised, could be unsupervised, or it could be other mix of supervised and unsupervised learning. Of course, we are not going through all these type of learning algorithms. We are going to go through mostly the multi-layer perceptron. I used to go through the radial basis function networks. If I have enough time proceeding with the lectures, we will go very briefly on radial basis function networks, but mostly I'm going to focus on the multi-layer perceptron and the parents of multi-layer perceptron, which are the singular perceptron model, and then multi-layer perceptron to lead us later on to more complex connectionist model in the form of deep learning systems. And then we are going to talk about unsupervised learning. This is a very important component of a neural network, namely a learning mechanism of a neural network. And because of the restriction of time, we are going to go over one specific unsupervised learning algorithm, namely the coherent self-organizing network, because there are several types of insights we can extract from this particular type of network when we are doing the learning. If we have time as well, we will go to auto-associative memories, Hopfield neural network, possibly restricted Boltzmann machine. We might not have time to do that. I usually don't teach that components because I usually do it in a graduate course when we have more modules to go through. But I will possibly talk about it, what it is, the Hopfield neural network, and what is an auto-associative memory, which is a component of supervised and supervised or hybrid learning model. So these are the learning paradigms in general. I shared with you last time the tree that is composing machine learning type of systems. So we are going to see two of the major ones, supervised and unsupervised. Semi-supervised, as I told you last time, is going to be in between these two type of learning paradigm, and we will go through it at least a few slides to showcase you how to utilize semi-supervised when we have a portion of the data that is labeled and another portion that is unlabeled, and how to go back and forth between the two type of modules to structure the semi-supervised type of models. So yeah, we spoke about the supervised learning last time. Also, we have seen this picture. I mean, the supervised learning model, mostly you have a particular engine, you have an input signal, you have a target signal, which is the labeled data with which you are utilizing to train the model. And then you have the actual output of the system, which we would like to be as close as possible to the target signal. So during the training process, we would like the output signal of the system to be as close as possible to the target signal. And if it is not, then a feedback mechanism is going to feed this particular connectionist engine, which is the structure of the neural network, with certain type of information, namely known as the weight updating mechanism. And during the weight updating mechanism, we are going to see how we do it. And this is the essence of machine learning using connectionist model. So we would like this error to be minimized starting from a certain type of level. We would like it to shrink more and more and more and more until it becomes below a certain type of threshold, which gives you the optimal value of the weight. And I say the word optimal because we are going to utilize an optimization process during that particular system. So I'm not going to go over it much, but we are going to deal with it later on when I'm going to introduce to you the training algorithm today and in the next few lectures. the error, the computation between the desired and actual outputs. The actual output is the actual components of the output system. It could be close, it could be far away from the desired or the labeled type of category of the system. So we repeat the steps, 1 and 2 here designed in the training algorithm several times to complete what we call an epoch of training. We will go to that word again when we are going to see the real world training algorithm for perceptron and later on for multi-layer perceptron system. And then we keep repeating this particular process until we reach training error that is below a certain type of threshold. And the process doesn't end here. So this is only the training algorithm. There is a testing stage, which we are going also to discuss later on, to make sure that the model that we have used for training is effective, not only for the data that we have presented to the system for training, but also for data that the system hasn't seen in the past. And these are called validation type of data, which lead us later on to testing data, which is the process by which we determine the model that is going to be utilized later on for the real world application. So there are several types of processes which we are going to see later on. So unsupervised learning, which we are going to tackle later, so I won't go over it today because we will go back to it. But unsupervised, as I mentioned to you, so you have an input signal and we have an output signal in the form of a set of clusters. And in between them, there is a mechanism that is updating the weights or the structure of this neural network so that these type of categories are bounded with each other in a very robust way. So we have only clusters that represent a family of input data together. And this type of system is called categorization or more formally clustering. So we cluster various amount of input data into the same category or under the same cluster according to certain type of features with which we have defined this input signal. So we are going to see also the mechanism, and especially we will talk about coherent self-organizing map because it's very visual and it provides us with better capability. Let me tell you, there are tons of algorithms out there, even in the area of connectionist models, and I am going to give you the fundamental ones because those ones are going to be utilized to build the multi-layer perceptron, to build a deep neural network system. So I would like to give you the fundamentals, and later on I will give you some reading, or you can explore yourself on these particular type of algorithm. So very quickly here about the unsupervised training. So the training data is presented at the input layer. So these are the 4 stages. Output nodes, which are the categories or the clusters, are evaluated through specific criteria. So this is the criteria that we are going to select so that we are going to have nodes of the output of them is represented through, they are categorized according to similarity in the form of their attributes. And the only weights connected to the winner nodes are adjusted. This is very true for the self-organizing map, which we are going to see later on. And of course, we are going to repeat the process several times until we reach a steady state behavior of particular type of error, or what we call performance index of the system. So here we have also an optimization type of process. So we will see all of this later on. Reinforcement learning, I described it last time, so I won't go over it. I have shared with a number of you some reading material about reinforcement learning. It's not going to be part of this course because it is being taught in other courses. And it's not part of this course anyways, even from the early structure of this particular course. So the overall idea is the input outputs are connected with each other through reinforcement type of process, and the reinforcement process dictates that the output signal, according to the output signal, whether we provide the connectionist model with a reward or with a penalty according to the output. So from a certain set of training data, the system either reinforces the system, provides a certain type of reward, or provides a certain type of penalty to say that, no, the output is not what we are expecting from the system. This is a major learning algorithm that is used especially in the area of gaming, in the area of application for a wide range of data, as I described last time in the application of reinforcement learning system. So I will go to the fundamentals of neurocomputing. I gave you early on the history of how they progressed to where we are now. So number 6 here is the most recent milestones, which is deep neural network system, which we are going to discuss later. But this as the progress of neural network in the past few decades. So here we are not mentioning the latest growth of the system when we have the growth of deep learning models. So we went from the simplest model, McCulloh Pitt model, to the Adaline model, to the backpropagation algorithm model, to the BPL2 model, which is the more powerful multi-layer perceptron model, to what we are seeing nowadays, deep learning models. And we are going to go through all of them. So let's go very briefly about what is the McCulloh Pitt model. So we said that we would like to create first a boundary between two types of classes. How this boundary we could create it. So we could create it through a certain set of training system. There are a number of techniques that have been utilized even prior to these dates, utilizing certain techniques in naive-based approaches, or using principal component analysis for as applied to supervised learning systems, although principal component analysis nowadays is mostly applied to unsupervised models. But there were techniques which we call them the early age of pattern recognition type of systems. So this is the first connectionist model that has been proposed in the mid-40s and on which people have built what we are seeing nowadays, the growth of neural network system. So this system is simply a connection system where we have input pattern vectors. So we have several types of input systems connected to, multiplied by a certain set of weights. There is what is known as the bias input. I will explain to you what is this bias input. Remember that this bias input is an artificial input that the model only goes through origin, as it is the case when we have only this particular type of input data, but the system also could go through the off origin of the plane system composed of all these type of dimensions. So this is a pattern with L dimension. And then what we do, once this type of data have been summed with each other, then we have an activation function. An activation function in the very early model of the McCulloh Pitt is no other than a sign function or a signum function. The difference between a sign function give us value either negative or positive. So it's -1 or +1. The signum function, the step function. So there are two aspects. So there is the signum function, the sign function, and there is the step function, as we saw earlier. So the step function gives us an output of the system that is either 0 or 1. The signum function provides us with a value that could be -1 or +1. So whether we utilize the negative components of the space, or we go either from 0 to 1, which is basically the step function. And I will give some examples later on this, but signum function or step function are completely equivalent type of activation function. So what does that mean here for this very, very early model? Whether the output belongs to one class or another, as simple as that. That's what this earliest model provides us. And this is provided through the choice of these particular weights. As you can see in these particular weights, there is no mechanism that we are utilizing to optimize them or to tweak them automatically. They are tweaked manually. And this is an extremely difficult process to make sure whether a pattern belongs to one class or another. So we have set of labeled data with input pattern, with an output pattern, and we try to manually change this particular type of value so that our training type of data falls in the right class. Once we have this particular type of data, we are hoping that data that the system hasn't seen in the past is going to react in the same way as the training data. So this model is very, very simplistic. It's very, doesn't have mechanism for learning, so it's not a learning model. So it doesn't have a machine learning capability. So this is the functionality very briefly. So we have a L set of input models. You have hard-coded, as I mentioned, manually coded omega 1, omega 2, which are the weights. And we have also a hard-coded bias term that is going to provide us with the value that is going to be equal to one class or the other. So F here is the activation function, and it is completely discrete value, whether it is signal function or the step function. So this is how the system works. Usually what we do, we incorporate this particular bias into these weights in an artificial manner, so that instead of having this complex type of function, we have only omega I times xi, but instead of starting from 1, we start from 0, similar to this particular representation. So this is an artificial way for including the bias term within the summation term. This this is, I mean, the most simple type of system, as I mentioned to you. It is manually tuned system, and it's very complex, and it has not been used in any type of application. So it was possibly an early version of a connectionist model to mimic how possibly a cell in the brain is working. So that was in the mid-40s, in the early 50s, And then people said that this cannot be utilized. This system cannot be utilized as long as it is not automated. So then Rosemblatt and colleagues have come up with a supervised learning algorithm with which the tools for extracting the weights of the system are provided automatically, as we are going to see. And this is the first machine learning model utilized in connectionist models, the Perceptron. So the Perceptron is the first machine learning model. It's not an optimized one, as we are going to see, but it is first one. So it could be the father of all machine learning we are seeing today. That is called the Perceptron type of models. And for this particular model to work, the patterns have to be linearly separable. What does that mean, linearly separable? It means that there is, I mean, a line in the two-dimension case, or a hyperplanar multidimensional decision boundary that classifies the pattern into two classes. So there is a line, so it is a plane, it is a hyperplane. So the plane is not nonlinear in its formation, and we are going to see that this is one major shortcoming of the Perceptron, as we will see it in few slides from now. So this is what we mean by linearly separable. So the separating boundary is linear, as simple as that. That's what it means. So you have class 1 and the class 2, and if the separation line between both of them, we call them linearly separable. I would like you to remember this word. So there is linearly separable, and later on we are going to see for the multi-perceptron model, multi-layer perceptron model, we are going to see the non-linearly separable pattern similar to this. So this is the non-linear type of behavior that is separating between the two classes. This is very generic, and this is very powerful. But in the days of the 50s, the 60s, even in the 70s, we did not have any type of tools to create these nonlinear separable type of patterns. So for now, during the 50s and the 60s, we are constrained to create only a linearly separable type of behavior. If the data is nonlinearly separable, we cannot utilize any type of tools in the field of neural network. That's why the perceptron is still being used nowadays for certain type of applications where we feel that the data is separated by a linear type of boundary, whether linear, whether it's a planar, whether it's a hyperplanar type of model. People could utilize very easily perceptron model. You don't need to have very, very heavy multi-layer perceptron model, or you have models that is using deep learning type of characteristics. You don't need to do that. And that is my comment at the later part of machine learning model using connectionist systems. If your system is simple enough to be separated, use the perceptron. If your system is a little bit more complex, use the multi-layer perceptron model. If it is extremely complex with a huge amount of data, then use the tools of deep learning systems. I would like you to remember what I just said. So you don't need to utilize multi-layer or deep neural network systems if your data is simply separated by a linear type of boundary. I will come back later on to this particular system. So this is the structure of a perceptron. So the structure of the perceptron is now more complex, but it's more visual, as you can see it, and similar to what we have seen in the McCulloh Pitt model, but it has a major difference. The major difference is that we are, after the actual output, we are utilizing the actual output, what the system has generated. We compare it with the target output, so there is an error. And then this learning error, we utilize what is known as the Hebbian rule or the learning mechanism, similar to what is happening in our brain in terms of reinforcement of the signal, not reinforcement learning, but reinforcement of the signal that is being transmitted from one cell to the next is being made using the Hebbian rule system. I will discuss that later on. But for now, this particular mechanism, which gives feedback here to the system. So this is a system with feedback. And as you remember from control system theory, a system with feedback is a system that is usually stable, a system you can stabilize, especially if the system is observable and controllable, then the system could be stabilized. So this is a system that is being auto-tuned on its own. So you don't need a human that is going to tune up for you these particular type of values because the system is utilizing a feedback mechanism. We are going to see later on an improved feedback mechanism, which is the early generation of the modern machine learning systems. Because even with this Hebbian learning system, we are not utilizing a powerful type of mechanism that is going to provide us the most optimal values of these particular type of weights. But for now, we have a feedback system, we have an auto-tuning type of system that is able to generate for us certain type of class. And this was a major discovery in the 50s. And this perceptron, which was developed by the work of Rosemblatt, has been utilized and has been even implemented in certain type of application during the 50s, early 60s, up to the early 70s when we have major issues with this particular model when we try to implement it to more complex type of structure. So this is what the system tells us and what the perceptron convergence theorem tells us. So the perceptron convergence theorem tells us simply, and I would like you to remember these theorems. So there are not many of them that we are going to see in these lectures, and these could be utilized during the quizzes or whatever. When I ask you what is the perceptron convergence theorem, I would like you to remember it very well, especially, look at this particular definition. So what we say here, if the training set is linearly separable, it means that the two classes could be separated by a line, a hyperplane, or by a plane. Then there exists a set of weights for which the training of the perceptron will converge in a finite time, and the training patterns are correctly classified. So the system tells us, this theorem which has been proven, it tells us that as long as you have two type of classes that could be separated by a line, okay, by line, so this is training type of data, this is training type of data. So you can see that a line could separate between these two type of data. And you tell me how we are able to do that. I will show you how to create this, whether this system is linearly separable from the training type of data or not. So this line, as you can see it is expressed in the form of x1 and x2. So it's exactly a line in the two-dimensional type of cases. So the minus theta here, this minus theta, allows us to have this line away from the origin. As you can see, when you have two classes, you don't have to have the two classes, the boundary between the two classes passing by the origin. So that particular bias term, which we spoke about, allows us the capability of doing this particular offset or bias. And this is a very important component. We have to always train our model so that this data is very well defined, as we are going to see it in the next learning mechanism for the perceptron. So I would like you to remember this slide very well. So it has two type of classes, and there is a linear type of boundary that is separating between the two classes. So it's simple, it's easy, but I would like you to remember it because we are going to see it later. So as you can see, this particular line has been now transformed in the form of x2, which we usually call it y, is y omega 1 divided by omega 2, theta omega 2. As you can see here, for this two-dimensional system, we have three parameters. We call them the hyperparameter of the system. So these are the parameters that we need to extract through a learning system so that this line is differentiating between the two type of boundaries. I'm not saying optimally separating the two classes, because the perceptron doesn't do optimal type of separation. The perceptron provides you with a way of separating the two boundaries. It doesn't say that we optimally separate them. So we are going to see other more powerful algorithms besides the perceptron algorithm that is doing the optimization. We will see also later on the gradient descent type of algorithm that is going to be utilized for separating between boundaries, not of two classes, but multi-class systems. So this is the training algorithm of the perceptron. I don't want you to be scared from this set of steps, but we have only 5 to 6 algorithms in the connectionist model. This is one of them, and this is one of the original type of algorithms. So this algorithm says that you initialize the weight and the threshold to small random values. So we don't know what are these values, but you give small random values, I mean, from the start, and then choose an input-output pattern. So you choose the kth input-output patterns. So most of the time, the input pattern in the perceptron, x is a vector and t is a scalar. Why it's a scalar? Because t could be either 0 or 1. So in the case of the step function as the activation, or it could be -1 or +1 if we are utilizing the signum function. So we select one training pattern, we compute the actual outputs with utilizing these random values of omega i's and the theta, and then we adjust the weights of using the perceptron learning rule, which is namely the Hebbian learning rule. So I would like you to remember that the perceptron learning rule is no other than the Hebbian learning rule. The Hebbian learning rule has been discovered by neuroscientists and by Hebb in the early 50s. And Rosemblatt utilizes that particular Hebbian learning rule for this artificial perceptron system, which is an artificial neuron. So what we call it perceptron. So this is the first artificial neuron, and we have utilized for this first artificial neuron the tools of neuroscientists to provide us with this particular type of rule. So the system says that from one stage of the training to the next stage, so we have now random values, and then the next stage when we are injecting values of the inputs and xik, tk, the improvement is going to equal to a real value between 0 and 1 times its coefficient times the difference between what the target is supposed to be and what the actual value it is. So this is what is supposed to be. This is the labeled output, and what the output is of the system times the value of the input. So this is, if we look at the Hebbian rule for the real type of neurons, it says that the improvements of the weights or the activation weights between one cell to the next one is proportional to the difference between what the system has generated and what the value of the input or the strength of the signal in the input. So this is well known in the area of neuroscience, the Hebbian learning rule. The same applies for the bias term. So delta theta is equal to the reverse of tk minus ok. So you can see here still the proportionality, but this particular value minus eta here, it's give us the value, the negative type of components to illustrate that the changes in the theta goes against the difference between the output of the error between the TK minus OK. So this one has been also artificially done, and the minus sign was also artificially added to make sure that this particular type of components for the system is able to utilize that. Why we are doing the minus here? Let's look very, very briefly at this particular theta. So this particular theta, the system says minus theta. It could be plus, minus theta, where theta is positive. But here we are presuming that theta is a positive number, and we are doing the minus. So this make it compatible to the sign in front of the omega I xi, which is this particular value times xi, the delta. The second one is you can see that the tk minus ok is similar to the value of delta omega I. So why we are doing the minus here? If we were going to include the theta within this particular type of summation, then this particular one could be augmented to this particular area, because this particular area is going to become multiplied by xi, and it becomes the function from I equal to 0 to L times omega I xi k, where omega 0 is equal to theta. So this is an artifact that has been utilized by scientists to generalize the algorithm. So that's why this particular minus sign. So the system tells us here, if the value of f is the signum function, so whether it is minus or plus as output, okay, this particular value becomes equivalent to delta omega I equal to 2 eta tk xik if tk different than ok, and delta theta is equal to minus 2 eta tk. This is very easy to mention. Why we are doing that? Because we have this f, and this f could be 1 or minus 1 according to this particular values. So what we are saying here, that if this particular value tk minus ok, if the ok is equal to a signum function, whether it's plus 1 or minus 1 for this particular system, then this is going to be equal to tk minus ok if it is different. So if tk is different than ok, and if the ok is the value of the minus is the signum function, then we are going to have tk minus ok, tk minus tk, which gives us the value of 2 eta tk xik. So this becomes 2 eta tk if the value is different. So if the system is generating a value that is different from what the system has been trained with, then you have to have a strong value of the update of the weight. That's what the system tells us. So this is the feedback that we are generating. However, if the system has generated the value that is similar, tk and ok are ok is similar to the value of the tk. As you can see here, tk minus ok becomes equal to 0, and this is the value of 0. Okay, so this is otherwise, which means that the target output is equal to the actual output of the system. So this is very important type of update function, and this is the earliest learning rule that has been developed in the field of machine learning systems. As we are going to see that this is not an optimal one, it's not a robust type of one, but it allows us to create, nevertheless, this boundary between the two classes. Of course, the same thing, we do it for delta theta. We say that if tk is different than ok, then it's equal to minus 2 eta tk. Simply because if the ok is different, because it becomes equal to tk, so if it is different, so then it's equal to minus tk. That's what it means. And minus tk, it gives us the value of 2 tk. Okay, so that's what we mean by this particular value. So now what we do, we go through as many values as possible from this set of patterns. So we present the first pattern, and then we present the second pattern, we present the third pattern, and we continue training the system as we go. So if we have 10 patterns, we have to go through all the patterns of the system, as I'm going to give you an example later on. If after we train all this type of pattern and the system has delivered to us at the end of the day value of the delta omega I equal to 0 and delta theta is equal to 0, then we say that the system has been trained, and the final values of the omega i's that we have trained and we have updated, that those values are going to be utilized are the separating values of the system. So the system ends when delta omega I equal to 0 through the whole epoch. So basically, after training of all this type of data, then we say that the system has learned its line, hyperplane, or plane if we are going into multi-dimensional type of space, especially when xi is not a scalar. So this is basically what we have in the training of the algorithm. It's a simple type of algorithm. It is, again, I would like you to remember, it is based on the Hebbian learning. So we are going to see other type of learning that is more powerful than the perceptron system. So this is a very simple example. So we have class 1 and the class 2. As you can see, the class 1 has a target -1. Class 2 has a target of +1. And we have several patterns. So for class 1, we have T, we have U and V. Class 2 has X, it has Y and Z. So again, following the algorithm, I'm not going to go over it I will go over it very briefly to illustrate what we have seen here. And we start. So we start with these random values. Usually the random values are smaller values than 1 or -1. But here, for illustration purposes, we take them as the extreme values. Omega 1 cannot be selected more than 1. The omegas cannot be selected more than 1s or -1s. Higher than -1 or smaller than -1 are always within the range of 1 and -1. So usually they are random variables. And theta is equal to -1. Also, it cannot be selected as less smaller than -1 or higher in the absolute value. So the initial boundary, as you can see, utilizing these particular parameters, which were taken as as random values, -1, 1. So we have selected -1, 1. This could be +1. This could be -1. So this is the boundary that we have selected. So x2 is equal to x1 -1. So let's see that particular boundary. So this is the original boundary of the system. This is where T, this is where U, and this is V are located. So this is the first class. This is the second class. As you can see, with random original values, this is the boundary. As you can see, this boundary only is a wrong boundary because it only classifies T. However, V and U, which should be from in this particular side, are not classified. So this particular boundary is not the right one. And the training of the algorithm tells us so. So it says that T is properly classified. So T is properly classified from this particular side. However, the system tells us that U is not well classified. So what we do, we update the theta, we update the omega to provide us with the second version of the updated boundary, which is equal to -3x1. So this is the new boundary. Okay, and we have gone now through only 1 and 2 type of value. So we haven't gone through the V, the Z, the X, and Y. So for this particular example, to make it short, we have this particular boundary. Now, if we check whether Z belongs to the second class or whether VU belongs to one class, so we can apply the value of omegas, omega 1, omega 2, and the value of theta, and we found them that they have satisfied the well-classified version of this particular system. So once we implement the value of delta omega 1, so is equal to -2, so then we can extract delta omega 1 and delta omega 2. What are the updated value of omega 1 and omega 2 from one stage of the training to the next stage of training? The same thing for delta theta, and the system gives us this updated boundary. So now if we check with all the T, U, V, X, Y, Z, we find all of them classified either from one side of the curve or the other one. So the green line, as you can see, has classified as VUT and ZXY in the right way. So this particular perceptron learning rule was able to classify for us and update for us the value of the weights. As you can see here, for this particular type of algorithm is completely different from the algorithm that we have seen in the very original and the simplistic McCulloh Pitt model, the one that was discovered in the late 40s. Why? Because this is a rule. There are rules here that provide us with ways to create this perceptron. Remember this perceptron that was discovered, I mean, in the early 50s, in the late 50s and 60s, it was improved, is still being used nowadays in certain manufacturing cells, in certain type of applications where the data is crisply separated by a boundary that is linear or hyperlinear in case we have multi-dimensional type of systems. So I would like you to remember this one, this system, and certain remarks here. So this simple layer perceptron suffers from two major shortcomings. Although it gives us a good boundary, but it is not able to separate linearly non-separable patterns. It means patterns that are that cannot be separated by linear type of patterns. Okay, so linearly non-separable patterns or nonlinear separable patterns are equivalent in the context of this particular system. So it means that with a linear or hyperlinear system, the patterns cannot be separated. Okay, it can be only separated with a nonlinear boundary, as we are going to see later on. Lack of generalization. This is an important component that we are going to see in the multi-layer perceptron system and also later on in the deep learning model. Once this system has been trained, it cannot adapt its way to a new set of data. So what it means here, that because there is no optimal type of rule here that provides us with the best possible pattern. What does that mean? So this with this particular rule that provided us with the green line, as you can see, it is very, very close to Z. So later on, if we are going to have a pattern that is similar to Z, but it's located in this particular region, because the system is not optimal. So as you can see, the system was not able to separate it in this particular way. But we should expect in the future that something in the generalization components of the system, something might be close to Z, and yet it's going to belong to this particular area. So then you have to redo the training of the system from scratch with the type of new data, which is which is not very good. So this algorithm, while it serves its purpose for a certain type of application, it's not generalizable. And we are going to see that major components of machine learning system that we need to have major over generalization of the data with which we train the system. This is going to be a major aspect of this course as well later on when we are going to talk about overfitting, underfitting, overtraining, undertraining of the system. So this particular system is not optimal. It doesn't provide us with the best boundary. In my case, for instance, if I was, a scientist, I would say a line that is going to come this way here. So let me do it here. I don't know whether I can do it here or not. No, this doesn't allow me to do here, unfortunately, here. So no, I don't have a line that I can utilize here. But if I use a pattern here, that goes through this way, that pattern would be more powerful, the boundary would be more powerful than the current boundary. Simply why? Because we are going to expect in the future, for generalization purposes, to have certain areas possibly located in this area, because you can see that it is close here, it is close here. So we don't want to have that. We are going also to see in support vector machine how to optimize this type of boundary. Support vector machine is another tool that I spoke to you earlier today and last time that is excellent for doing classification, optimal classification boundaries. So not only we would like to have boundaries, but we would like them to be optimized. Okay, so that's what we mean by lack of generalization. I would like you to remember this word. So first, the perceptron cannot separate linearly non-separable patterns. Secondly, it is not optimal. And we are going to see why it's non-optimal. I tell it to you now because we are not using a formal formula that is utilizing an optimization mechanism, and it doesn't use a performance index, which we would like to optimize it to get to the best possible weights. We are going to see that later on when we are going to tackle the Adaline, which is the more powerful system of the perceptron. So Adaline, which is the better version of the perceptron, it is more powerful system, and it has been a big improvement of the perceptron, and it is good generalizer. Why it's a good generalizer? Because it gives us the best possible type of boundary that with which we can generalize. So even if we have additional data in the future, we know that the boundary is very far away from the two classes, so that the boundary is always able to generalize and always able to fit between the two classes. So this is an important aspect, and this is a major difference between the perceptron and the Adaline. So it is also more powerful in terms of weight adaptation. Why? Because this is the first time we are going to see in this particular algorithm that we are going to utilize a formal way of optimization. And the formal way of optimization is the simple gradient or the gradient descent, which is going to become the tool of excellence for machine learning tools when we are utilizing more complex structure of connectionist models or more complex structures of deep learning type of models, the gradient descent. So the gradient descent has a gradient descent algorithm for dealing with machine learning systems using artificial neural network is applied here for the first time for the Adaline. And that's why I go piece by piece to showcase you that machine learning using the machine learning tools of nowadays did not come from the void. It came from a whole succession of successes and failure. So we have seen the failure of the perceptron, that it doesn't deal with generalization very well. It doesn't have it doesn't deal with nonlinear type of separable type of platform. So we are trying here to see what are the power of Adaline, whether it solved the generalization problem, whether it also solved the problem of dealing with linearly non-separable type of classes. So we are going to see that in a few moments. So the Adaline is very simple. It is similar to the perceptron type of model. As you can see, the major difference between the Adaline and the perceptron, I mean, very easy to see, is that the feedback with which we are feeding the synaptic weights here doesn't come from the output of the activation function, but it comes from the value before the activation function. So you can see here that we have exactly the weights. We have the input, we have L inputs here, we have L weights. So we have the same feedback mechanism. The only difference is that we are not taking the signal from the target. So the target here is no other than the target is no other than the labeled type of signal with which we are utilizing it to train the model. Remember that in order to create these type of weights, we have to utilize the label type of data, the input and the output. So we train it so that later on we are going to validate it with data that the system hasn't seen. And we have seen in the perceptron that we train the system, it gives us a very good type of boundary, but ultimately when we are going to test it with data where it is a little bit farther from the system, we are going to discover that the testing of the data is not going to be satisfactory and the model is not going to be valid to implement. So that's why we have to revamp it and we have to utilize better type of algorithm. So this, what is known as least mean square learning mechanism. So least mean square, there is, I mean, reason why we call it least mean square learning algorithm. This is the baby version of what we call today gradient descent system for system. Least mean square is based on the derivative of the error mechanism. So we would like, remember, we would like that our error from one side, from one aspect to the next aspect, from one update of the weight to the next update weight, we would like that error to be minimized. Not only we want it to be minimized, we want it to become very, very small, but also you would like it from one training set to another training set to another training set, it doesn't change much. When we see that error hasn't changed much through the very training type of sets, it means that the function is at a local or global optima of the system, depending on how the error function is going to be composed. So then we say that the system has converged. And when the system has converged, it means that we have optimized the error. So the error is at its bottom value, and then we say that the system has been trained. So why this is major importance between this part and this part? Simply because the output of this particular error, remember that the t is equal to either 1 or -1. And remember early on that the value is equal to -1 or 1. So the error could be, in this case, could be either equal to 2 or -2 or equal to 0. So 2, -2, or 0 are values. You go from -2 to 2, let's suppose, I mean from one value to the next, and 0 in the form of the error. This is discrete. 2, -2 from one stage to the next stage, or 2 to 0, or -2 to 0 is going to be discrete. Remember, the characteristic of a discrete system, we cannot utilize the derivative of a discrete function, a function that jumps from 1 to from -2 to 0. This function, when you when you would like to look at the derivative is equal to infinity, and we cannot utilize this learning mechanism. So that's why in the Perceptron learning algorithm, we were not able to utilize a formal optimization method. However, in this case, remember that the target is equal to +1 or -1. But at the outset of this perceptron, before we go to the activation function, this value has a value. It could be a continuous type of value. So a continuous value with a particular bias, it's always a value that we can do a certain type of gradient. We can do a certain type of derivative. So the function doesn't jump from large value to small values. So this is providing us with the capability of using a gradient or derivative type of function, which we are going to utilize it in this particular function. So I would like you to remember this one, similar to what I want you to remember, the optimization, the perceptron theorem, learning the Adaline. So the Adaline is an improved version of the perceptron. And this improved version of the perceptron is giving us what is known as the least mean squared algorithm, also known as the Widrwo-Hoff Learning algorithm. I would like you to remember that the LMS squared algorithm and the Widrwo-Hoff Learning rule are exactly the same, because the LMS algorithm was proposed by Widrwo and Hoff in the late 60s, early 70s. So this learning algorithm now is going to utilize, look at these words, optimization, gradient descent optimization. So this is a formal way for minimizing an error. So now we are mathematically based. We have a performance index. We have a base, mathematical base, with which we are going to extract this particular weight. So delta omega now is no other equal to minus theta times tk minus ok. Now look at it beautifully. It's equal to minus eta times the gradient with respect to the vector omega of E omega. And E omega is the performance index. That's the error. That's the mean squared error. So we would like to minimize the mean squared error of the system with respect to the vector omega. And that's why we call it a gradient. Remember, when we are deriving a function of multivariable with respect to its various multivariable, we call it gradient. However, when we have a function with one single variable and we would like to create the derivative, we call it simply the derivative. So the gradient is the extension of the derivative, and it is a vector. So the gradient is a vector. So it gives us the decay of the error in various type of direction. Remember that the derivative of a function, it's like a vector with respect, it's the tangent at a particular point of the function. The gradient is multi-vector composition for a function that is multivariable. And remember that the E omega here, EW here of the weights is a function of multivariables. So that's the first thing that we need to know here about the Adaline. So the Adaline is very powerful and it's able to provide us with this capability for doing the derivation. So let's look at this particular function with which we would like to do the derivation. So learning in the Adaline. So the network total error ECW for all patterns xk, tk, as you can see, we have to collect the error for all the values of the system, okay, for this particular model. So this is what we call the batch learning. So what we mean by the batch learning, we sum up all the training type of data for the system. So this is what is known as the batch learning. We are going to see also the online learning, which is going to be different from the batch learning. We will come back to the batch learning later on when we are going to look at the multi-layer perceptron. But I would like you to remember what is batch learning. Batch learning is the cumulative error for all the patterns is injected into this particular function. So as you can see, we have the TK, but also we have the summation of all the training type of data. And this is what is called cumulative, E-cumulative. So we have to add all the values. And as you can see, the values of all this type of training data. So what we do here, we create all the errors. So we check the error 1 for the first training point. We check the error 2 for second training point, error 3 for third point, error n for the end points, and we agglomerate them all together under this cumulative error. And then we try to do the gradient descent for this cumulative weight. Okay, so this is one way for training, and we call it batch training. We will come back to this definition later on when we are going to use the multi-layer perceptron. However, we can do the online training, and the online training is no other than taking one training data at a time. Training data at a time. This is what we have, EK. So EK stands for the kth training pattern. XK and TK is computed. So this is the error, the online error at a particular element of time for this particular training data. So for each element of the data, we have a K. And then the individual weights are updated using delta omega is equal to minus eta gradient descent with respect to EKW, as you can see here. And the value for this particular system is no other than this particular form. So this particular form is not extremely far from what we have seen earlier. The only difference, as you can see, is in this particular type of component. This particular type of components, before it used to be the OK. What is the O superset OK? It was the output of the system after we apply the activation function. You can see here that this is the error before we apply the activation function. Let me go back 2 slides before. Look, this is the TK, this is target K, minus the output of the system at this particular level. And this function is completely continuous function. So we can utilize the gradient for that particular function. For the perceptron, we have utilized the feedback from this particular level after the system goes from the activation function, which generated an error for which we cannot do the gradient descent. So that's the major difference between the Adaline and the perceptron. So the Adaline, remember, provide us with an optimal way for providing these delta omega I. This is very important. So for the first time, we are speaking of an effective machine learning system that is providing us with an automated value of the weights. Remember that the weights and the bias are fundamental values of the system. And these type of weights are extracted using a mathematical type of rule, which is given by the gradient descent. Remember that this gradient descent, we are going to see it later for even larger models of the neural network. So I want you to remember this, very important, even later on when we are going to tackle the deep learning systems. This is going to come back and we are going to analyze it and we are going to utilize it. Noted here that we haven't used minus theta. So what we did simply, we utilized that artifact where the theta is now involved as part of the summation, where we utilize the xi as an artificial input, value of -1, and where we include the theta as equal to minus omega 0. So then this is plus omega 0. So now instead of starting from I equal to 1 to n, so now we're starting from I equal to 0 to n. So that's why we don't have the minus theta. So for those of you who are questioning why we are not using this theta, so because the theta now is involved in this particular type of value for the system. Otherwise, the theta is going to be located here. Okay, so this is now the algorithm of the system. So this is very similar to the training algorithm for the perceptron. The only difference now is this updated formula. This is the first known machine learning model for connectionist modeling systems. And it has been discovered in the early 70s when people have come up with the major disadvantages of the perceptron, that it's not a good generalizer. So what does this system do for us? This system is able to generalize. Why? Because we are minimizing, we are obtaining the omega I according to an optimizer, which is the gradient descent. Remember, the gradient descent is optimizing a performance index that is composed of that particular error. Let's look at this error again. This is the error that we are utilizing for the system. So we are utilizing this particular rule, again known as the Widrwo-Hoff learning rule. So the first, if I ask you what is the first learning mechanism that has been discovered in the field of connectionist modeling, you say that the Widrwo-Hoff learning rule, or also known as least mean square rule, LMS type of rule. The perceptron has also its rules, but it is not optimal. We don't have a performance index to minimize. Okay, so that's the major difference between the two systems. So here we have the same type of training. The only thing that we have this particular LMS learning rule for the models. After we train the system several type of times, and then we reach a value of delta omega I equal to 0, then the system tells us that you have been able to train the whole system, and now it is up to you to validate and check whether the model is safe or not, to commercialize it or to use it for further type of application. So the major advantages of the least mean square algorithm are easy implementation, because it has it's based on the gradient descent or the optimization of the error. It is suitable for generalization. Why? Because it's going to provide us with the optimal boundary. It's going to provide us with the best possible boundary that is going to be located between one particular component of the data and the other type of components, which is a missing feature in the perceptron. So the major difference between the LMS algorithm and the Hebbian learning rule is this. One is perfect for generalization, the other one is not optimized and it cannot be used for generalization. So this is the Adaline, but remember here that we haven't talked about linearly non-separable space. Is the Adaline able to do that? Adaline is not able to do that. Why? Because it is based again on linear type of boundary. So if the data is not non-linearly separable, then the Adaline is not going to provide us with the major boundary that is going to separate between the two classes. So let's look at it again. Shortcoming of the Adaline. So the Adaline, while having attractive training capabilities, which provide us with the optimal setting between the two type of classes, or the two type of classes in a linear form or in the hyperplanar form, it suffers from the inability to train patterns belonging to non-linear separable space. So if the space, if the two type of classes cannot be separated by a line or a hyperplane in the multi-dimensional case, then even the Adaline is not able to solve this problem. So this was a major setback in the early 70s when people, breathed a sigh of relief. The Adaline is good generalizer, but still it's only for linear type of boundaries. So people have tried to come up with improvements on the Adaline. So they have tried to create multi-Adaline type of units, and they call them multi-Adaline units. So how they do that? So basically they create Adaline 1, and they create Adaline 2, Adaline N, and then they try to concatenate all of these type of Adalines that are trained with the various particular type of weights, and then utilizing certain type of logic gate to provide certain type of output. So in other ways, what we are going to use, we are going to use a set of components of linear or hyperplanar type of boundaries that are going to be compounded with each other so that they are going to encircle classes on their own. So we don't use Perceptron 1, Perceptron 2, Perceptron N, because we say that Adaline are better suited than Perceptron. But in order for us to qualify Adalines for separation of nonlinear separable space is to utilize component of representation of a system. And the best possible model that we have utilized is the exclusive OR function. So here we have the exclusive OR function. So let me see here if we have figures. So I don't have figures. So I usually do this on the blackboard. So I don't have a blackboard here, but I will provide you with 1 or 2 pictures to showcase you how to separate between the between 2 non-linearly separable classes. So for this particular system, as we saw in a set of slides last time, we have the exclusive OR. The exclusive OR is one of the approaches of the gates that cannot be linearly separable. So it is a certain type of data. Let me see here if I am able to extract some tools here. PDF comments, let me check here. Okay, so let me utilize here certain line here. So for this particular system, so let's suppose that we have, okay, so 0 and 0 here, the system provide us with a class. For 1 and 1, the system provide us with another class here. And then for the other class, for 1 and 0, the system provided with another class. And here the system provide us with another class. So as you can see, this is the exclusive OR. So this should be here. So I'm going to fix this one. So this should be a 0 here, okay? It's not -1. And this should be 0, okay? So I will fix this one, okay? Because we are dealing with in the positive part of the space, okay? So here in this particular, or this one, we could have this instead of -0s, and we can utilize them as -1 to become compatible with this particular value. So I will fix this particular table here so that we are compatible with this particular representation. So here we can see that there never be able, so if we are trying to do this line, it's impossible to separate between this class because this one is located here. If we do this line only, we are separating this one, but this one belongs to the other class. So what we are doing here exactly, we are utilizing Adaline 1 here and Adaline 2 here. And we combine both of them together using an Adaline 3, as you can see in the figure here. So now with this line here and this line here, we are able to separate between this class of the O's or the zeros and this class of these type of elements. So we can see that the Madaline is able to solve a problem that is related to non-linearly separable type of formula. So we are utilizing these ones because we are not able to, so let me undo this one. So yeah, okay, so I'm not able to undo this. So the other possibility is to provide, instead of 2 Adaline, is to provide a nonlinear type of boundary that goes this way. Okay, now forget about these 2 lines that are the Madalines. So the other way for separating between this class 1 and class 2 is to provide a nonlinear type of boundary. But remember, these Adalines are created using a version of the perceptron, so they are linear in the form. So we are never able to create this nonlinear type of structure, this nonlinear type of surface. Okay, so the Madeline is not able to provide us with this particular nonlinear surface, and that is why even the Madeline, despite the fact that it's going to be able to solve this particular type of problem for using two Madalines or components or set of components of the Adaline, the system is not able to provide us with a nonlinear type of separable type of space. And this is why we are going to move later on to more powerful type of algorithm. So despite the successful implementation of the Adaline and the Madaline units in a number of applications, many researchers conjectures that to have full connectionist computational tools, models that are powerful, we need a better topology. We need more than one particular components of the perceptron or the Adaline or the Madaline. So the schematics of the Madaline implementation for the backpropagation system composed of multi-layered perceptron is going to be the choice that we need to apply to this particular system. So this tells us that with the structure that we have seen so far today, using the McCulloh Pitt model, which is, the very simplistic and the lowest quality type of perceptron, but it gives us ideas to the future. The perceptron is an improvement over the McCulloh Pitt model. The Adaline is a further improvement. It gives us better generalization, but it is still applying to linearly separable space. The Madaline is an artificial set of several types of Adalines that provides us with an artificial way for separating between classes that are easily could be easily tackled, similar to the ones here. But what about if we have multi-classes instead of two classes? What about if we have very, very close type of surfaces here, similar to here, so something here? How are we going to do it with Madalines? How are we going to utilize Madaline? And the answer to this, it's not possible. So even the Madaline, the most powerful set of elements of connectionist models, are not able to solve the problem of classification. And this requires a major type of architecture that we need to study. And this is going to give us rise to multi-layer perceptron, which are going to be utilized for the next, after 15 years from these type of developments. And then we are going to also to see the shortcoming of the multi-layer perceptron. And all of this, we are going to start tackling it for the next lecture. So I have a number of examples here, to utilize, for this particular system using the perceptron and using the Adaline. So I would like you to look at these type of examples. So I did not go through them here, but this is, using the perceptron, how to train the perceptron, and when the system is nonlinear separable, how the system is not able to classify the model. So this is a whole set of examples that I would like you to look at, and they are mentioned in the next set of slides. So this is again an example related to the perceptron, as I have shown you for the system. So for this particular system, the final values of the weights after 13 type of iteration, it gives us these type of weights. So I invite you to look at this example once you start reading the lectures. So I would like to end the lecture for today. And if you have a brief question, please go ahead and ask me. Otherwise, I will post the material for you as usual, and I will be happy to share with you the material. Thank you very much again, and I'll see you on Monday next week. Okay? Have a good day.